during the improvement of turbine performance in the companies or research offices of the companies that produce turbines. Experimental tests must be done on models because it requires less effort, less expenses, and less time. The performance of prototype, what is meant by prototype turbine, the original or large size turbine, the performance of this large size turbine, like what the performance, dimensions, speeds, speed of rotation, power output, efficiency, cavitation parameter, etc., can be obtained from the experimental data obtained with small-scale model tests by using similarity relation. These similarity relations are obtained using Buckingham Pi theory for dimensional analysis as presented here through several steps. Okay. Why we do this? Because the tests on complete tests on large turbines before installation is costly, time consuming, and also difficult, as the actual load flow rate and load cannot, actual head flow rate and the head cannot be varied easily in the turbine factory during the design stage, because it needs huge equipments, huge إمكانيات كبيرة. Tests on geometrically similar models of small size under all possible conditions, the result of these tests, plus similarity relation obtained by Buckingham theory of dimension analysis, then the performance of large size turbine can be attained easily with minimum cost and effort. This means that you can predict the performance of large size turbine without you have this large size turbine. Only you have a model of this turbine tested in a lab with small equipments, and plus the dimensional groups obtained from similarity relations obtained by Buckingham theory, you can obtain the performance of large size turbine easily with minimum price, minimum cost, minimum expenses, and less time. Rho n square, rho n d square over mu, which we call it Reynolds number, and epsilonality. Since we always use water in this turbines of the same density and viscosity, this means rho and mu are not changed. The results of experiments indicate that Reynolds number rho n d square over mu has no effect on the power, and also epsilonality has no effect too. This means from this slide that P naught over rho n cubed due to power 5 will be only function of Q over n d cube and GH over n squared d square. If we know that, you can say that if you keep Q over n d cube constant, this means Q over n d cube for the model equal Q over n d cube for turbine, and also for GH over n squared is kept constant. This means for this value for model will be equal to that for turbine. We must set that P naught over rho n d cube over rho n cube due to power 5 must be constant also. Actually, we have some problem here. If you have epsilon near 1 or around 1, P naught over rho n cubed due to power 5 will be equal constant. But if the dimension ratio between turbine and the model greater than 1, we can find that the effect here of epsilonality and of the model will be greater than that of turbine, and this means that the hydraulic losses in the model will be greater than that for turbine. It will, and consequently, the efficiency of turbine will be greater than the expected efficiency for model. How can we obtain the turbine efficiency from model efficiency? There are empirical formulas. We call it as we have several empirical formulas. Modi formula Modi formula states that 1 over minus turbine efficiency over 1 minus model efficiency equal d to model divided by d turbine to power 0.2. This means that you can obtain eta turbine from eta model if you know the ratio of dm over dt, scale ratio. Also, we have Eckert formula, which combine the effect, the turbine efficiency with model efficiency and the ratio of model diameter to turbine diameter and head of model to head of turbine. We have several here. The second one is preferred Fleder efficiency or Fleder empirical formula. We can obtain that turbine efficiency is function of model efficiency and Reynolds number of model and Reynolds number of turbine and diameter of model to diameter of turbine. Wotton empirical formula, efficiency of model and Reynolds number ratio, Reynolds number of model to Reynolds number of turbine, you can obtain efficiency of turbine. As I think we call Eckert number related efficiency of model with efficiency of turbine and Reynolds number of model and Reynolds number of turbine. Okay. We have some definitions about GH over N squared D square. We call it head coefficients. We give it simple psi. P over N cubed due to power 5. We call it power coefficient. Power coefficient. Q over N the cube. We call it flow coefficient, and we give it phi symbol. Actually, GH over N squared D square means head n dimensionless form. P over N cubed D to power 5 represents the power n dimensionless form, and the Q over N D cube represents the discharge n discharge n dimensionless form. We have figure, the following figure indicates the effect of turbine size on the efficiency, which what we call it scale. Here as we see, the efficiency curve and the head against charge, head coefficient and flow coefficient, head against flow coefficient. This means the head n dimensions form against Q, and the efficiency, as you see here, the square, the hollow squares represent the full scale turbine, which has a higher efficiency at any discharge. When we small scale model of circular, hollow circular, we can find this is the minimum efficiency. This means the efficiency increases as the size of turbine increases for the same flow ratio. Actually, the sketch shown here represent the performance test rig used to evaluate the performance of model. It consists of two tanks. The lower tank, the pump, suck the water from lower tank and give it to about overhead tank, then to the turbine, and then to downstream tank number 6, and then again to tank number 3. This turbine here connected to brake test facilities like dynamometer. We can use the torsional force, and then from it we can obtain the torque. And this also speedometer, you can obtain from the torque, and speedometer you can obtain the power of output of that model at different, either at different H or at different H. H here is a difference between the head level in tank 8 and tank 6. This is a head H. Also, we can change this head, we can change this discharge, etc., and we can obtain the effect of H and Q on the performance of that model. Also, we can also test the model for cavitation, or to work under cavitation in order to get the cavitation coefficient. We call it sigma. We have here a closed circuit system. We have a tank number 3 full of water, and the water from this tank can be transferred by a pump number 6 to the turbine number 2, and then this will be the dynamometer and the measuring scale of the force which we can obtain from it, the torque torque output from that turbine under the test. Also, we have here a speedometer. From speedometer and torque, we can obtain the power output of that turbine. Under the test, we can see that Venturi meter can be used to find the discharge, and also we can see here number 10 represents vacuum pump. Vacuum pump can affect the vacuum or the ambient pressure inside tank 3 above the water surface. This means we can affect or can vary the pressure outside the turbine in order to subject it to cavitation. For this lecture, you have a homework, 5 problems, 1, 2, 3, 4, 5, and I am ready for your questions. Thank you very much.